Welcome back, everybody. It's lecture number 6. We're going to talk about optimization today. But before we get into that, I'm sure that you would like to know some things about our upcoming midterm exam. So it's going to be at October the 30th. That's a Friday. It's the end of week 4. And that is the nominal time, but you will actually be able to take this exam anytime inside of a 48-hour window. So it's going to go up onto Canvas and you will take the exam on Canvas. And it's going to be available at the first minute of Friday, and it's going to go away at the very last minute of Saturday the 31st. And those times are California times. So once you begin the exam, you will have 1 hour to complete it. So you won't be able to go back and redo it or something like that. The exam is open, so whatever resources you need to help you, but I do have to warn you that there's not going to be enough time if you have to look up every single thing. So don't take that to mean you can just not study, right? And I'm sure that you are going to study because I've heard quite a lot from people that some of the math is really not quite clicking. So to study for the test or to better understand the math in general, please do come and ask questions at the discussion sections or the office hours. Ask on Piazza, right? You're going to need, I think, a bunch of different times. I'm sure if something is really opaque to you, you'll have to probably get it re-explained to you 5 or 6 different times from different people. So please do come and visit us. Now, while you are doing this kind of stuff, I'm sure you will be glad to know that there is not going to be any homework assignment in week 3. So we've got one that's going to drop here tomorrow tomorrow as I'm talking. I don't know when you're listening, but this Thursday you have to turn in a homework assignment, and that will give you a new homework assignment for the Thursday after. But in week 3's Thursday, there will not be a new homework assignment, so you will not be dealing with a homework in week 4 when you're trying to study for the exam. Okay? Let's see here. So thank you very much for filling out the form that I sent around, the Google form. I was hoping to get a little bit of feedback, and I did. As I mentioned, some of that feedback was that what people are panicking most about, of course, is the math. It seems like the concepts and the nature of the homework and so on is much less commonly a problem. It's really like people seem to often talk about being worried about fully understanding the math or making sure they get it right on an exam. So it's about as expected. Also about as expected is I'm glad that everybody's about okay with how fast the lectures are covering material. Definitely the largest category. Well, let's see if we can keep up that nearly perfect record by being nearly perfect with optimization. Oh, that was a lame joke. I am so sorry, people. It is late. All right, dad jokes done for the day. So basically, machine learning really is optimization in disguise. And we're going to chat about this several times, but this is the time where we get to really dig into what the math is. All right. So this particular lecture is going to be like a little bit like the last one, kind of math heavy, but I'm going to try to make sure that we clearly explain everything at the intuition level, okay? And none of the math is very complex this time. So, well, let us start at the beginning. And that beginning is the monotonic function. A monotonic function is something which never goes backwards, okay? So, for instance, a line. A line is going to move always forwards, right? And once it, the slope doesn't change, so it can't bend back on itself. Now, another monotonic function is an exponential. So an exponential is always growing this way, and it never turns around and comes back down. Also, a log, a natural log in this case. A log function is also monotonic because it never turns backwards. But there is a big distinction to be made between the different ways in which these functions operate, right? I mean, a linear function is always increasing at a constant rate. The exponential is continually increasing its rate, and it, eventually really asymptotes at some point on the x-axis. And a log is the opposite. It asymptotes on the y-axis, right? The linear function and the exponential can reach infinity, but this one can't. Okay? But yet, because it never turns back on itself and goes down, then it is always going to be a monotonic function. So when we say monotonic, we can say monotonically increasing or decreasing, okay? So if you have a monotonically increasing function f of x, is the negative of that function a monotonically decreasing function? Stop for a second and think about what your answer is. My answer is that if I was doing this about 2 hours ago, I would make you do a little pop-up interactive quiz here, but instead, I'm just going to give you the answer, which is yes. Yes, indeed. A negative of a monotonically increasing function is monotonically decreasing, and I think you can very clearly construct that image in your head. So, if you have a monotonically increasing function, f, okay, and we're going to restrict it to be in the positive reals, so no negative bits to it, is the natural log of that function monotonically increasing? All right, question 1 for you. Why did I restrict the function to be in positive reals? Yes, you in the front row. Yep. It is because a natural log of a negative number, or more to the point of a 0, can be quite difficult to deal with, right? Okay, so so the question is the natural log of a monotonically increasing function also monotonically increasing? Survey says, yes, indeed. Yes. So if you take a monotonic function and apply it to a monotonic function, the result is monotonic. Okay? So if you add together two monotonically increasing functions, f and g, are they? Think about it for a second. Come up with your own answer. That answer is very clearly yes. Okay. So this one's a little different. I'm cueing you here so you can pretty much guess already, right? So if x and f and g are monotonically increasing functions of x, is f minus g monotonically increasing? It depends, right? It depends at their relative rates of increase. And clearly, if g is a quicker increase than f, then it can overwhelm f and start to bring things back down and make a non-monotonic. Okay. So, why are we doing this? I said this was going to be about optimization. Well, realistically, monotonic functions are an important building block for a lot of machine learning theorems, and that includes how optimization gets done. So as long as we know that a function is monotonic in its behavior, that generally introduces either something that makes our lives much easier or enables us to reduce the complexity of the math and its implementations. All right, so an example of that is this math. So what is this math? I have never seen this before, right? So what it is, it's a math describing clustering. So if you have a bunch of data points that exist in a space, and your job as an algorithm is to assign points to colors. We're going to say that in this case that some process is making these orange things, and a different process is making the green things, and a different one is making the blue things, right? So one way to go about doing this is to take the values of x and come up with a probability distribution describing how likely it is that the label of this point right here is orange, or whether it's blue or green. Okay? So in that case, the thing that we're trying to do is trying to figure out the most likely of the assignments of the labels for each point. Now, the math here is obtruse and beyond the scope of what I'm trying to do, but fundamentally I just wanted to give you a flavor of why we do this, okay? So to try to find out all of the points, what their likelihood is as a unit, right? So we're trying to make the clustering give the most sense, give the highest likelihood answer for all points. So for when you have a probability like this, which is the probability of the label given an input and the current parameters of your cluster assignment, well, that's just going to be the product of all of the points probabilities. It's going to tell you the total likelihood of the total probability of these assignments. Well, that's a pain in the butt to calculate that. So first off, this is a multiplication, which makes your life hard. Secondly, there's going to be, you would prefer to be able to separate out the influence of each individual point, right? So if instead we take a natural log of this product, right, then what happens is the natural log of a bunch of multiplications becomes a summation of natural logs. So just a reminder of basic calc kind of stuff. So this natural log of a product becomes a summation of natural logs. Things are now splittable. Turns out that additions are easier to calculate than multiplications, especially when you're doing kind of nested loop kind of stuff, which you may do in clustering. So again, I know that that was probably not a full explanation that made it sufficient for you to understand everything about clustering, because clustering itself is a topic for another course. And we haven't been talking at all about this kind of notation of conditional probability, right? But I wanted to give you the flavor that the reason we do monotonicity is that it can make calculations easier in terms of being separable and also in terms of computation, like in this example. All right, so monotonic functions, they are cool. So you notice there that I used notation called argmin and argmax. So these terms you will see over and over again because they are fundamental to optimization and machine learning. So what we want to do in any kind of learning situation is we want to get the best answer, right? We want to get the best model, or in the case of what we've been talking about it recently, the best parameters for a model. All right? Well, to do that, we want to maximize something, right? Or minimize, depending upon how we couch the problem. So if we're going to ask the question, who is the richest person in the world in 2019? Right? The answer concerns the person, not the amount of money. Okay? So if we say we want to find the richest person, then what we're trying to do is we're trying to pick the argument value, which is which person, which will maximize the function net worth of that person. Okay? So the answer is Jeff Bezos. He is the richest person in 2019. I forgot to look it up for 2020. And at that point, he was worth more money than you should reasonably have as a single individual. All right, so the important part here is that the argmax function is finding the right value of this argument, which will make this value here be the highest. Okay? And I think you can guess what argmin does. So the poorest person in the world would be argmin person net worth. Okay, so the richest person in the world becomes Jeff Bezos. And again, if we were picking max of net worth, the max net worth would be the money, the billions of dollars, right? But we're picking the argmin, find the argument which minimizes or maximizes something. So, it's pretty cool that these two flip, 100% around. So if you want to know who is the poorest person in the world, we can either do an argmin, or we can do argmax of minus their net worth. Okay, so the richest person in the world is the person who has the lowest poor rating, right? And the poorest person in the world is the person who has the smallest rich rating. So negative of the function involved is the same thing as the argmin. Okay. So, what does this look like? The operator is going to show you the optimum value of a function L. Okay? By the way, why do you think we call it L? Well, the L function is short for loss function. And, the world of optimization of functions covers a lot of ground. But one of the places it came out is in economics and statistics, where they often use the word loss for anything that's not optimal is a loss compared to optimality, right? So you will hear loss function, you will hear error function, you will hear objective function. These are all the same thing, okay? It's a function we're trying to make the best it can be. So in this case, we're going to use the notation L for loss. And in machine learning, people will usually say loss, although like a decade and some ago, they would have said error. All right, so remember, argmin L, just like argmax, doesn't return the value, it returns the argument. So the parameters W, which produce the lowest value of the loss function, are going to be returned by argmin of W. Okay, and in this case, let's just say that W star is there. Okay, so the W star is this location on the parameter space, and the lowest value that the loss function attains is this value over here. So this is min of else of W, and this is argmin of else of W. Now, cool thing here, this notation, the star, you'll see over and over again. Sometimes you might also see something like a caret or a hat or whatever you want to call that. The idea here is that you need a notation to say this is the optimal value, right? So the optimal value of the weights are the weights which minimize the loss function, which makes our loss the lowest that it can possibly be. Okay, so sometimes you couch getting things the best they can be in terms of attaining the highest possible value, right? So in that case, you can use argmax. And as we were already saying, it's just the flip side of the argmin, right? So these are actually can be equivalently notated. We can say here is the highest point, and this value here is the maximum of the function of, in this case, g for gain, right? The gain function, something we're trying to make the highest it can gain to. Okay, so here is the highest, the max of the function, and here is the argmax of the function. It's the w star, the optimal parameter. Okay, so optimization for argmax looks a lot like argmin. It's just things flip around, and we can make them the same with a negative sign. Okay, so good stuff. How can we do this as kind of a definition, right? So a function is, if a function is monotonic, right, then we can say apply it to an argmin or an argmax and expect to get the same answer. All right, let's go through the values on this. So if a function is monotonic, and a definition of monotonicity is that for every v1 and v2 that we have, if v1 is bigger than v2, then it is always true that the function of v1 is bigger than the function of v2. This is true for a monotonically increasing function, right? As you go from left to right, I hope I don't have that ruined in the camera. Okay, from left to right, you will see that the higher values on the number line better produce higher values of y value, okay? So in that case, whatever value minimizes the loss function will also minimize that monotonic applied to the loss function, okay? So the transformed version of this loss function is transformed by a monotonically increasing function. Then we're going to get the same best value whether we're applying it to the loss or whether we're applying it to the g of the loss. Why are we doing this again? Well, remember that by making things monotonic, we can potentially manipulate them to make our lives easier. All right, so here's an example with numbers, and I'll get my face out of the way. All right, so let's make up some arbitrary monotonic function. This function is a function that is essentially a line, right? 2 times v plus 10. So it's a y equals mx plus b situation. All right, so in this case, w star, the optimal value, is going to be the same, getting the argmin of the loss, and it's also the same when you do 2 times the loss plus 10. You will always, in both these cases, doing the argmin will give you the same best answer, the same best parameters. All right, this is also true if we use another monotonically increasing function like a natural log. And I've already kind of given you a hint that natural logs are a good way to make things easier to deal with. So, and when you do a natural log, you can take, if you're going to maximize g, right, maximize this natural log function, then taking the natural log of that function is the same as doing an argmin negative natural log of the function. Okay? These are just examples to give you an idea of how we can apply this kind of both monotonic functions and the argmins and argmaxes. Okay? Consider this practice. I'm not showing you exactly how something works. I'm giving you an idea of operations that you will see again later. So, I want to hark back to my first lecture. And in that lecture, I took the silliness of saying, okay, let's ask Google, what is machine learning, right? And autocomplete suggests that it's a bunch of possible things that are all really fairly simple. And it's an ongoing joke that really machine learning, it's not that hard, right? It may just be regression. It may just be a bunch of if statements. That's a reasonable take. But in the end, the most simple, the most general formulation of machine learning, as I said during that first one, is it's really just picking the right model and then minimizing the loss function to fit that model the best possible way. And now you have an idea of what we mean when we say that, okay? So, machine learning, I will tell you, is optimization, okay? So remember how we're kind of formulating our problems. The test set error is the training set error plus a generalization error, right? And so ideally, when we want our best possible machine learning algorithm that we could possibly make, it's going to do no error on a test set, on a set of data it's never ever seen before. Okay, but we know that we can't check that in advance. We know that, in fact, what we have to do is we have to minimize our error on the training set. Okay, we want to do well on the testing set, but we know that if we check the testing set, we're going to overfit the data and we're not going to generalize well. So we have to operate on the training set, and we have to hope that by minimizing our error on training set, we are also minimizing our error on testing set. And that will be true up to a limit. And we will figure out where those limits are and talk about how to fix that as we go through the quarter. Okay? So we're going to try to minimize training set error, and we're going to do it using the same kind of decision boundary loss function we were talking about one lecture ago. Okay? So if we mislabel something from our decision boundary, so this is the prediction of our decision boundary, right? That is the output of our classifier. And if it is wrong, if it's not equal to the true y value, the true label, then we get a 1. We've misclassified, okay? So for every sample in the data set, in the training set, we are going to add up all those 1s for anything that we missed. And then we're going to normalize by the number of items in the training set so that we can get an average misclassification rate, okay? A mean rate of misclassification is what we're doing right here. So, in general, what we are trying to do is to find the parameters W, right? We're trying to find those that minimize this function. That defines the loss function for the decision boundary problem. Okay? So, as I mentioned already, kind of got ahead of myself, this error is defined by the loss function we choose. Okay? So if you choose a different function here, which is possible, right? You can choose a different function. This is not the only way to fix a classification problem. Then you would be optimizing a different kind of loss function. You would be defining what it means to make an error differently. Okay? In this case, our definition of an error is, for instance, I don't care how badly you've misclassified. I just care that you misclassified. Let's imagine a classification problem where we were trying to classify dog breeds and cat breeds. Okay? In that classification problem, we're trying to say, is it a a poodle or a Doberman Shepherd? Is it a Manx cat or a Siamese? All right, so if you misclassify, if you don't get a Siamese right and you call it a Manx, is that maybe less bad than calling a Siamese cat a Doberman? Okay, so this loss function we have here doesn't care how badly you've messed up. It only cares, did you mess up? But you could write a different loss function which cares about how far away from the truth you were, if there was some sort of metric there that you could use. Okay, so I'll just give you an example that the error is determined by the loss function. The loss function tells you what it means to make a mistake. Okay? So, it's important to note that the algorithm actually consists of both the model, which is the W parameters, right? And it also consists of this loss function. So, this part is the model, but so is all of this. So when you pick a different loss function, you are doing a different algorithm, essentially. And you can indeed, there are machine learning algorithms which share the exact same format for the W vector. The W vector has the same interpretation fundamentally, right? But they use different loss functions, and so they are different algorithms. So, once again, I will remind you, machine learning really is just picking the appropriate model and then minimizing the right loss function. Okay. So, our goal, like we're saying here, is to find the process that gets you the least error, right? This is actually old. I didn't want that in the slideshow. That's why I was hesitating. All right. So ignore that, and let's just say we want to recap the nature of optimization. Okay? The intuition is that there's some function that's going to be minimized or maximized. And in fact, they are equivalent, right? We can turn argmin into argmax with a negative sign, and you can take any shape like this and just turn it on its head, and you will get the same transpose, right? You'll be able to do it as a minimization or as a maximization, just depending upon putting a negative sign on something. And the math is to use this, and we can do it in a variety of ways, because in the end, it's not just that we are optimizing something, it's how do we get an optimization done. And how you do this depends upon the function you are operating on, okay? So loss functions that have a certain format, they can be solved analytically. You can just solve with a closed form for the right parameter W that makes this value the lowest possible. But for other kinds of loss functions that have a different form, that's not possible. You have to blindly search or search with some principles through the space of possible W parameters and see how you can find one that minimizes this argument. So this is a huge, complicated field. There are entire textbooks and courses out there, like this one is one example, that lead you to the methods and techniques of how you actually optimize different kinds of functions. And then beyond the math, there's implementation details as well. So different function formats have different optimization tricks. And then even once you've got an optimization trick that you're using, you also need to implement it computationally on a machine. And then there's all kinds of algorithmic tricks for doing it the fastest way possible and stuff like that. So it's a huge field, and loads of people need this kind of stuff because it's not just machine learning. Business stuff uses optimization things, right? A lot of the origins of this come from trying to optimize the flow of products or stuff like that in linear programming. Okay? Trying to optimally determine how to allocate your resources to do things the best way. Okay, let's give some definitions that we're going to use. So, in general, when we're trying to optimize some function, we can talk about it having two kinds of minima, okay? Two kinds of minima. You could have a global minimum, which is the lowest point for every part of this function which is defined, okay? So some functions, it's trivial, right? The minimum of a line is negative infinity. And that sucks because we don't care, right? But what we want to find is we want to find somewhere in a finite band of possible values in the parameter space. What is the parameter which best does things? So that's a global. However, your surface that you are operating on, your error function or loss function, it could have multiple dips and wiggles. So we can also define something called a local optimum. Now the local optimum is going to be the best solution somewhere within a neighborhood, okay? So within some neighborhood that we're going to notate as cursive n, within some neighborhood around a point, the point is the local optimum if it's the best answer inside that neighborhood. Okay, so the last bit is just to note that we are talking here about omega, which is the set of all optima. What is an optimum? What is an optimum? Well, it's the point at which something is low. And as we mentioned the other day during the regression thing, right, an optimum can be found by its derivative, okay? Anytime the partial of w with, the partial of the loss function, w, with respect to w is equal to 0, then that is an optima. That is a local optima or a global optima. We don't know. Whether it's one or the other depends upon these definitions that we just talked about. Okay, so if it's the best one for all of the loss function defined across its whole support, then it is a global optima. If it's only the best answer within a neighborhood on the support, then it's a local. So again, and that, the same derivative trick is true right here as well. Right. So what can we do? Yeah, I was like, that slide shouldn't have popped up. I'm having all kinds of slide issues today. All right. So how can you solve one of these optima? Well, there are a ton of algorithms, and these algorithms could take lots of forms. The nature of which one you pick depends upon the kind of loss function you're trying to solve, like I was saying. But broadly speaking, they come in two flavors. Ones which get you the answer in a fixed number of steps, or ones which try to find it through iterative motion. What does it mean to find something iteratively? Well, you start out somewhere and you explore the space, right? The idea behind this loss function, whoops, I want this instead. So the idea behind the loss function here is that you are just going to start somewhere in the state space and you're going to follow some rules which cause you to go down a gradient and end up in some minima. Okay, this is the very nature of gradient descent. You just kind of fall down the hill. That's defined by this loss function. And the way gradient descent works is largely with the same kinds of physics as a ball rolling down a hill. Now, if you start over here, you might end up in this local minima. And if you start over here, you might end up in this global minima, in this deeper, darker red. Okay, so what's an important take-home on all this iteration stuff, right? The deal is that you can't just look and see the whole fitness landscape, okay? This loss function has bumps and curves. You have to check it out. You have to explore it. Now, you can explore it like we were just talking about with gradient descent, where you try to roll down the hill until you can't roll down the hill anymore, okay? There are other ways to explore a loss function to find a minima. You could just check every point that exists exhaustively. That's very hard, but you're definitely going to find the global optima in that case. Or there's a bunch of other techniques like evolutionary algorithms or various kinds of trying to find different versions of the gradient descent that enable you to take into account ways to kick out of this minima. But again, that's kind of beyond the scope of this course. We will talk about them a little bit, but realistically, like I said, it's an entire separate course about how you find the right algorithm to do a particular optimization task. All right. So if a function is of a particular form called convex, it makes the optimization way easy, okay? We love convex functions. So what are these things? Well, you probably had some geometry and you probably have a vague idea that a convex thing is a cup, okay? Something which is a bump is concave, but really a convex cup and a concave concave cup and a convex bump. God, did I mention it was late? All right, so a convex bump and a concave cup are the same thing, just flipped 180 degrees. So a convex function is either one of these two, okay, if it has that kind of shape to it, a cup-like or bump-like shape. But let's formalize this. So the first one of these is a convex function. This one is not. Why is it not a convex function? Well, if you look, there's parts of it which are concave and parts of it are convex, okay? And if you have a mix of the two, it can't be a single convex function. Let's do another version of this definition, okay? So this is a convex shape. Because it doesn't have any part which is going upwards, okay, in the middle. Let's formalize this. Okay, for drawing, so if we want to know, is a shape convex, the way to do it is to draw a line across the shape. Let's take a look. So if we draw a line here from W0 to W1, and essentially if everything that lies underneath that line is the function, and no parts of the function go up above that line, then it is a convex shape. Okay, so let me use the actual slide graphic instead of me talking about it and drawing on it. Okay, so we can do this, what I was just drawing for you, right? here is a chord across a function going from 0 to 1. And any point that lies on the loss function under that should be less than that chord line for this to be a convex shape. Think of it like water going in the cup. Okay? It's a cup shape if wherever the water level is going across the shape, all parts of the glass of the cup are underneath the water surface. That makes it cup shaped. If any parts of the cup stick up out of the water surface, then it's not a cup shape. It's got a bulbosity, I'm just making up words here, but a concavity rather than a convexity. All right, so to formalize the math fully, what we're defining here is the line from W0 to W1, which is defined here. Okay? So anywhere along this part down here, which is defined by that, has to be less than any part of this up here. So the path, the loss function of W0 and W1, and you put this A in here. And this A lets you go back and forth along this line. Okay? You're mixing the two values. So when A is 1, then AL sub W0 is L sub W0. Right? And when it's 1, this term disappears, it becomes a 0, and this goes away. So we're using that value there. And when A is a 0, then this term is maximal. It's just the L, the loss function, and this term goes away. Okay? So that A lets you move back and forth along this line. And likewise, the A here lets you move back and forth along this curve defined by the loss function. Okay? The same thing happens. The A lets you move back and forth. So we're saying that these two endpoints and anything on the line between them has to be greater than this path here, right? The loss function of this line, okay? So that's defined by the inequality down here at the bottom of the page. So whenever something on the left-hand side is greater than or equal to something on the right-hand side, for all possible pairs of W0 and W1 that you can pick, okay? If there is not a way for you to pick points on the curve that this gets broken, then it is a convex function. If, on the other hand, you can pick points on a curve that do break it, like in this case, then it cannot be convex. Okay? So when we pick these points here, then this is not convex. Let me notate that, W0, W1. And here is a point where the right-hand side is bigger than the left-hand side. All right. So the math can get a little hairy. So I'm not asking you to solve that theorem, right? I'm showing you the definition of convexity. So you should be able to recognize the definition of convexity, and you should be able to potentially apply it, but I'm not going to ask you to derive it, okay? All right, so convexity. Is this thing that I'm showing you on the screen a convex function? A little pop quiz. Did anybody notice this bit over here? So what do you think? Yes or no? Or it depends? The answer is no, because you can fit that chord right there, and that bump is sitting above the chord. Okay, is this a convex function? It is indeed convex, but it's not strictly convex. So strictly convex is when this is a greater than symbol. A just plain convex allows it to be greater than equals to. Okay? So what does that mean? How is that getting applied? Well, take a look here. So I can pick these points as W0 and W1, and the chord between them is exactly equal to the loss function at those points. So that means that we are not strictly greater than. So what is that? Well, it turns out that there are certain times in machine learning theorems that you would like to have something be strictly convex. All right. So is this a convex function? I'll give you a minute, let you use your Sharpie markers on your computer screen. Okay, it is not a convex function because you can draw a chord where the loss function lies above the chord instead of the chord lying above the loss function. So, is this a convex function? Well, I've already mentioned that it is concave, it's the other way around. But as long as there's no change from concave to convex, which ruins everything, we can just flip it back around with a negative sign and fix the problem and make it convex. So, the problem is not that it's concave, it's that it is if it's concave and convex in different portions of the same function. Okay? All right, so why are we doing this? Well, we want to get to the best model. We want to find if something is closed form. All right, so again, there's a bunch of slides in here that I'd meant to exclude. Okay. So convex functions that are differentiable are a special class of functions for machine learning. Okay? If something is both convex and you can differentiate it, then its global optimum exists singularly. You have exactly one optima. It is only the global, and you can solve for it by taking the partial and setting it to 0. There is indeed a closed form solution. We can actually find the value and simply solve the equation and get the answer. Okay? So it makes life super easy. This means that what it is it has an analytical or closed form. So to do that, you know that the optimal weight is going to be some function of the training set and the test set. Okay? Whoops. So X and Y are your training data. Sorry, shouldn't have said test set. So X and Y are your training data and the labels for your training data. Okay? So the optimal parameter is just going to be some function of the data that you give it and the labels that you give it. So you get your model just solved in one shot with no iteration whatsoever. So, like I said, you want to do this, you just go ahead and set the derivative to 0 and you solve. So an example would be this loss function. Let's define a loss function that has a parabolic shape, w minus 3 squared plus 4. Okay? Well, let me ask you before we go to the next slide, what is the derivative of this loss function? Yes, you're right. It is indeed 2 times w minus 3, right? Okay, so now we can just solve. We can plug this in and just say equals 0. Just head on over there and solve it fully. So turns out that the optimum value comes at w equals 3. Okay. So again, I have something happen to my skip slides that they didn't get skipped. What we want is we want to check out what happens when we have non-convex functions that are differentiable. And that is not the right, there we go. That's the right slide, my goodness. So in the non-convex case, we've kind of already previewed it. Standardly, you're going to solve this with something like gradient descent, some sort of search algorithm that explores the space of W iteratively to try to figure out where some sort of optima exists. Gradient descent essentially relies on the fact of pretending that non-convex things really are convex-like, okay? If you had this kind of a situation, right, you knew you had this kind of a situation where it was non-convex, where there was bumps, where just starting up at one part of the mountain wouldn't, following it to its lowest point is only going to give you a local minima, not the best version, right? You know you would like to jump out of that local minima, ideally, and find the global minima. Well, gradient descent in its simplest form is only going to send you downhill. Okay? And that means you know you're going to get stuck in a local optima, whichever local optima is closest to you. Okay? If you start over here, you're going to end up stuck down here. And if you start over here, you're going to end up stuck down there. Well, in higher formulations of gradient descent, you have various things that try to kick you out of that local and let you find the global. But fundamentally, the whole thing about gradient descent is that in its basic form, it tries to pretend that your non-convex function is actually a convex function. Because the only way to solve with pure gradient descent and get the right answer, the best answer, right, is if it is truly convex. All right, so it's probably a little bit too much, but I'm going to, again, we're going to cover gradient descent in detail, and that stuff will become understandable in a future class period. Right now, I'm just trying to give you sense of it and to give you a preview that this is coming up, okay? Because for right now, we are stuck with convex functions and things which we can solve analytically. All right. So just to recap, convexity. It is the best thing we can possibly find in machine learning. Things which are convex can be solved analytically. And we need to be able to distinguish between different kinds of function types. And you can pretty much tell it by eye if you can plot it in 2 dimensions, right? Convex, this is also a convex function, but it is an interesting case. This is right here, this is a convex function which is not differentiable, right? So this is a case like if you had an error function that looked like this, you would not be able to solve it analytically because you don't have differentiability at this point right here. Okay, that's a hint. All right, and there are non-convex functions, things which just are too bumpy, have convex and concave elements in them together that prevent them from being solved analytically, and we know that we need to go after them with something like gradient descent. And we have concave objects, concave functions, which if they're fully concave without any extra bumps in them, they can just be turned into convex by flipping them around with a negative sign. Okay, so the interesting parts here is we can solve, this one's analytically solvable. This one, no. This one, no. And this one, yes. Okay? All right. So, just to recap, we can define convexity in a mathematical form by putting in don't like that. Right, by putting in a mathematical definition of the fact that any chord across any pair of points in the function where the function lies completely underneath that chord, that is convex. Okay? So if we pick points W0 and W1, then everything on the loss function itself between W0 and W1, that all has to lie underneath that. And anytime you have a function where points between 0 and 1 go above the chord of the function, then that is not convex. All right. Loads of math, late at night. Even my tongue feels numb right now. So I'm going to go take a break, drink some water. You all, I hope you have an excellent day, and I will speak to you at an office hours or in the next lecture. All right, good luck, and homework number 1 is going to be due on Thursday. Hasta.